Welcome. So now let's look at some shadows. A man 5 feet tall is walking at a rate of 3.5 feet per second away from a light that is 30 feet above the ground. When he is 7.5 feet away from the light, answer the following. What's the length of the shadow? So when the light shines, the shadow is over here. There's a relationship between the man and his shadow. That says 5. And the lamp. And the shadow plus the distance between the man and the lamp. Right? These two are similar triangles. They share this angle right here. And they are right triangles because things like people and lamps are perpendicular to the ground. All right, so using angle, angle, so I can get it up there. Angle, angle, triangle similarity postulate. The two triangles are similar. Whenever I write up there, it's never where I think it's going to be, so it's never straight. All right, so this is really just a geometry problem. All right, and so we're going to compare 5 feet is to 30 feet. Actually, I don't need the numbers in there, the units in there. 5 is to 30 as x is to x plus 7.5. We could reduce the 5 and the 30, make that 1 and 6. And so now we have 6x equals x plus 7.5. Subtract x from both sides. We got 5x equals 7.5. Divide by 5. X is 1.5 feet. So the length of the shadow is 1.5 feet. Nice little geometry problem there. At what rate is the length of the shadow changing? All right, so now we have this distance here, and that is changing. But this 7.5 feet, that was just for a moment in time, right? If the man keeps walking, which he is, this is changing as well. So we could represent that with another variable, right? Because both those values are going to change. That change is proportional. So this here, that distance, is proportional to this distance, and this distance is proportional to this distance. So we can set up a proportion showing that. And all of most of these shadow problems are going to be very similar, especially anybody who's walking away, it's going to be set up the exact same way. So at what rate is the length of the shadow changing? So x is to 5 as y is to 30. Now we could reduce, make that 1 and 6. We could cross multiply. All we've done is we've just changed the look of the equation. It's still the same equation. 6x equals y. All right, and so this is b here. So A was in red and B was in green. Let's see if I can get how much I can get on this one page. All right, so now that we have the equation, now we can differentiate. Let's talk about, before we take the derivative, let's talk about our rates of change. So, because there's a reason we're taking the derivative, we want to find a rate of change. And we know a rate of change. We know that the man is walking at a rate of 3.5 feet per second away from the light. So this y here is changing at a rate of 3.5 feet. It would be positive because he's walking away. If he's walking towards the light, then it would be negative because the distance would be decreasing. So dy dt is 3.5 feet per second. We want to find dx dt, how the length of the shadow is changing. So that's the one we're looking for. So we have we'll take the derivative. So the derivative of 6x is going to be 6 dx dt. Derivative of y is dy dt. So you can see these are really simple derivatives on these shadow problems because he's walking at a constant rate of change. All right, we're looking for dx dt, so let's divide by 6. So dx dt is dy dt divided by 6. So dx dt is 3.5 divided by 6. And that's going to be, they could give us a nice number, huh? 0.58 and a bunch of 3's. So over here, we'll write it, and we'll write it with our units, because you always should have your units. That's important. dx dt is 0.58333, I'll call it another 3, and that's feet per second. All right, so that's how the shadow is changing. All right, so he's moving 3.5 feet per second. The shadow has its own rate of change, 0.5833333 feet per second. At what rate is the tip of the shadow moving? So now, that's not looking at the rate of change in the shadow. That's looking at the rate of change in that whole that triangle there. So if we think about the triangle, this was x. This is 5. This is the man. I didn't write in the constants. So our constants. And I didn't write in our variables. Aren't I terrible? So I will do that. So x was the shadow. Before we go any further, y is the distance between man and shadow. We have a couple things that aren't changing, the constants. So these are the variables. The constants is the man is 5 feet and the lamp is 30 feet. So we should make sure we know that. So if we want to use the man height, we can just use 5. All right, we also have this distance here that's changing. All right, so when we're looking at the tip of the shadow changing, right, we're looking at how I'll put C right here. And I'm going to try to color code, so I'm going to write in blue, because I haven't used blue yet. Although I messed it up with rates of change. Just one little thing in black. All right, so C there, we have the man plus the shadow plus the distance all right, or excuse me, equals the distance. We can represent this as a right triangle, right? So I should write that in there. Oh, we'll just erase that. So together, I think I was going to write this first. The man and the shadow and the distance form a right triangle. So that means that man squared plus shadow squared equals distance squared. And this is what we're looking for. We're looking for the rate of the rate of change in that distance, because that would give us the tip of the shadow. So man is 5. The shadow is x, and we'll call the distance d. All right, so now we can take the derivative. All right, so the derivative of 5 squared is 0. Derivative of 2x, or x squared is 2x dx dt. And the derivative of d squared is 2d dd dt. We're solving for dd dt, so let's just divide both sides by 2d. So we have 2x dx dt divided by 2d would give us dd dt. And we could just cancel out those 2's, right? So that's x dx dt divided by d would give us d dt. There we go. That's a lot of d's. All right, so we'll solve it out over here. So we've got x, and x we found, x was 1.5. Times dx dt, that was that, 0.583333, divided by the distance. We didn't find the distance, but we could find the distance, right? Because we have our triangle there, and we know this is 1.5. So 1.5 squared plus 5 squared equals d squared. All right, 1.5, so if this was 15, they'd be 225, so this is going to be 2.25. Plus 25 equals d squared. So d is going to be the square root of 27.25. And we already have got some decimal approximations. What's another one? So the square root of 27.25 is going to give us 5.220. 1.5. I mean, there's really no, I mean, if we don't get a decimal equivalent, it's going to be really hard to combine anything. So, so now we have 1.5 divided by, times 0.5833333, divided by 5.22015, and that's going to give us dd dt, which is what we're looking for. And now let's just simplify that out. So we have 1.5 divided by 0.58, and a whole bunch of 3's, and oops, I put divided by instead of times. And if I put in parentheses, I could just hit my previous answer and divide by that whole amount. So we get 0.16762, and this would be feet per second as well. I wrote all over my beautiful triangle there. There we go. All right, so we've got A in there, we got B in there, we got C in there. How bad does this look if I put D in there? What if I do this? So it is color-coded, except for the one little thing that's not color-coded. Here, I write in purple, so I didn't use purple before. We could squeeze it in. At what angular rate must he lift his head to visually track the tip of his shadow? So, must he lift his head? Wouldn't he have to lower his head? At what angular rate must he lift his head? He would have to lower his head. So anyway, if he's looking straight ahead, which is what he should be doing, right, that's his angle. This would be the angle of depression. Right, so that's the angle of depression. That's congruent to this angle here, the angle of elevation. So this angle here and this angle here are, and that's a theta, are exactly the same. All right, let's get rid of some of the writing in here. So this here and this here are the same, right? So angle of depression equals angle of elevation. All right, so those two are the same. So this would be our angle because that's inside the triangle. All right, and let's use the little triangle because we have more information about the little triangle. So right here, all right, we've got we've got 5, we've got D, we've got X. Now, to me, I think I'd like to use the 5. And the reason I'd like to use the 5 is that's a nice easy rate of change there. That's not a variable, right? So if we can use a constant, that would probably make things a little easier. And then we could use the X or we could use the D. It doesn't much make a difference, but since they're both just as ugly, so really doesn't make a difference. We can either use the 0.5833333, or we can use the 0.16762. All right, I guess we'll use tangent. All right, so we have tangent theta. And at least X is a nice value and D is not. So that's a reason to use the X. So tangent theta equals, right, so it's going to be the 5, that's not changing. The opposite side's not changing, over our X, which is changing. So that one has to be a variable. All right, I think I'd like to multiply both sides by X and move the X over, because at least I'll have a product rule. So X times tangent theta equals 5. Now if I chose sine, I know I was going to have a variable in the denominator anyway, so it didn't make any difference. So I may as well just take tangent. All right, so now we will take the derivative, and we'll need to, this one will be a product rule. So u is x, and its derivative is dx dt. V is tangent theta, and its derivative is going to be secant squared theta times d theta dt. Can I fit that in there? I don't know. Maybe I should have used an extra page. I think the derivative is going to get me. All right, so it's going to be the first, x, times the derivative of the second, which is secant squared theta d theta dt. And then plus. The second, which is tangent theta times the derivative of the first. So that's going to be, I'm going to write the secant first, or the tangent first. So we have tangent theta, and then the derivative of x is dx dt. Now we're looking for d theta dt, equals 0. So let's subtract the tangent part. So we have, and I'm going to have to extend the board just a little bit. There. Tried to do too much on one board. All right, so now we have x secant squared theta d theta dt equals negative tangent theta dx dt. And now let's divide by x and secant squared theta. So d theta dt equals negative tangent theta dx dt divided by secant squared theta. Now we just got to plug in all our values. So tangent theta, and we're looking up at that triangle up above there, tangent theta would be over 1.5. So 5 divided by 1.5, is that 0.3? Or just 3? No, thought it was going to be pretty. So 5 divided by 1.5 is 3.333. And then secant theta is not going to be pretty. So either way, I'm not getting something not pretty. And so that's going to be what was D? D was 5.20015, the hypotenuse, over the adjacent side. So that would be that value divided by 1.5. So 5.20015 divided by 1.5 is 3.466, and that's going to round up. I may as well earn 7. All right, so now d theta dt, now just plug it in. So d theta dt is negative 3.333 times dx dt was off the screen. It's right there, 0.58333. Divided by 3.46677 squared. My shadow is blocking. 3.46677, and that's squared. All right, and that's going to be, so we got 3.3333 times 0.58, lots of threes, divided by 3.46677 squared. So I get negative 1.6179. Oh, excuse me, decimal's in the wrong point. So negative 0.16179, and that is radians per second. That's how much he'd have to lower. And so that makes sense that it's negative, because he has to lower. I don't know why it says lift his head. All right, he has to lower his head to see the shadow. It's on the ground. Well, that's everything here. Hope I didn't cram too much in here. We might look at one more problem, but not on this video. So thanks for watching, and bye for now.